a continuous curve, there is no zero. It technically goes to negative infinity. So when you have the CDF, it's basically whatever. So in the case of this one, your mean is 250, your standard deviation is 50, and it's going to give you the area under the curve from negative infinity all the way up to 350. So basically the left side of the curve from 350 down. That's how the CDF function always works. So if you need above, right, if you need greater than, then you're just going to have to do 1 minus those, that kind of thing. And then the other function you need to use is the quantile function. And the quantile function allows you to work backwards, right? So with the normal CDF, you basically say, okay, I'm going to give you the mean, I'm going to give you the standard deviation, and then I'm going to give you an X value, and then you're going to tell me the probability of having that value, i.e. you're going to give me the area under the curve to the left of that number. Well, the quantile function does that in reverse. You still give it the mean, you still give it the standard deviation, but instead of you giving it a value and it gives you the area under the curve, you give it the area under the curve and it gives you the value, right? So you tell it probability is 0.2, and it says, okay, here's the value that has 20% of the area to the left of it, right? So just like the CDF, it's always area to the left when we're talking about probabilities, right, on these curves. It's always to the left. So in SAS, all you have to do is literally copy this, paste it into a blank program, and then change the numbers and then highlight what you need to run. So like I have all of my probabilities in one program, and I've saved it here under programs. But if I want to run normal, I just come down here and I just highlight the normal rows and hit run. And then there's my probability where my mean is 250, my standard deviation is 50, and this is the probability that we're 350 or less, right? Or less than 350 is the same thing, but basically to the left of 350. Does that clarify it for you?
Yes, it does. Yeah.
Fantastic.
Great. Thank you.
Yep. Okay, anything else before we begin? All right. Well then, our last actual set of lecture notes. We've been dealing with the binomial curve, and now with this last week is when we get into the continuous random variables. And those are the biggies, because continuous random variables, those are the ones that allow us to do what we're kind of more familiar with in statistics: hypothesis testing, confidence intervals. All of those things are built on top of the normal curve, and they're built on top of the central limit theorem, which is built on top of the normal curve, right? So all of this comes back to understanding what a continuous random variable is and how we can work with it, right? So we have to remind ourselves that continuous random variables have to give us continuous data, right? And continuous data are things that are measured, not counted, right? Things that are counted are discrete, and those go into our discrete random variables like the binomial. Things that are measured are continuous. So heights and weights, right? Length of life of a particular product. So basically any expression of time, the elapsing of time, is considered measured and continuous, right? So when we talk about the lifespan of a particular product, or if we talk about someone's age, right? All of those things are a measure of time, how long time has elapsed. So those are always considered continuous. Some sort of experimental laboratory error, sure, because usually when we're doing an experiment in the lab, we're measuring something with some sort of instrument, and because we're measuring it, then the error we get will also be a continuous measurement. So when we have these continuous random variables, we always have a smooth curve to describe the probability distribution of that random variable. So just like the discrete random variable, where like for the binomial, you had all those little bars. It looked like a bunch of little histogram bars. The height of each of those bars represented the probability of each of those discrete values, right? It was the probability of getting a 0 or a 1 or a 2 or a 3, all the way up to whatever your sample size was, or your number of trials were. And if you added up the area of all of those little bars, those little rectangles, it would add up to exactly 1, because that's what probability is, right? It has to add up to 1. So the same goes with these smooth curves. If we have some sort of smooth curve that represents the distribution of this continuous random variable, right? So for instance, if we're talking about heights, this could definitely be a curve that would represent heights, because it would definitely be skewed to the right, because you would have super tall people, like NBA players would skew it to the right. And it would obviously wouldn't go negative, right? Because you can't have a height below 0. I mean, technically, you can't even have a height of 0. But you get the idea that you would have a distribution and it'd be continuous because they're being measured, and so the area under this curve ends up being exactly 1, because the area represents probability. So if you want to know the probability of being greater than a value, then you draw a little vertical line and it's the area above it. If you want to know the probability of being below that value, then it's the area to the left. If you want to know the probability of being in between two things, then you have 2 lines, right? And you're finding the area in between those. So for instance, something that would look like this, you go, okay, well, great. Of course, my pen is red, so you can't see it. So there's red, right? And so here's everything in between those 2 lines. So let's say we said this is like 10 and 15. Then this would be the probability of this measurement coming up between 10 and 15. And I should probably even use decimals, right? Like 1.0 and 1.5, right? To remind ourselves that we can have decimals with these types of things. We don't have to have decimals, but we can. So that's what probability is. It's basically just the area under the curve. And because of that, we know that there are certain properties of these distributions, that the total area has to add up to 1, because probabilities add up to 1. The probability of X, remember, X is the outcome of the experiment, i.e. X is the value of that continuous random variable. So the probability that that continuous random variable has a value between A and B is simply the area under the curve between A and B. Like I was trying to show with my previous example with my crappy little red lines drawn on a red graph, which didn't help so much. You'll notice that this picture says X is strictly greater than A, strictly less than B, but up here it's less than or equal to's. Well, they're the exact same thing, because the probability that X equals A is always 0, because if you want to know the probability that X equals A, there's no width. There's just the line above A. And since there's no width, there's no area. And if there's no area, there's no probability. And if you think about it, it makes sense, because if you have a random variable that is measured, which means it can take on any number between, let's say the lowest value was 0 and the highest value was 100. But it's not just the numbers 0, 1, 2, 3, 4, 5. It's all the decimals, right? So it's 0.1, 0.001, 0.00001, right? It's all those decimals in between. I think we all understand that even between 0 and 1, there are an infinite number of numbers when we talk about counting up decimals. So whatever your range is for your continuous random variable, it is going to have an infinite number of possible outcomes because of all the decimal possibilities. Well, obviously, if there's an infinite number of possible outcomes, then the probability of one specific number has to be 0, because it's 1 over infinity, right, for its probability. And so that becomes 0. So that's why the probability of anything equaling a certain value is always 0. And that's why we don't have a normal PDF function. Or we had the binomial PDF, a P as in Paul instead of C as in Charlie, right? The PDF function was when we wanted to know the probability of exactly, let's say, 3 successes out of 10 trials. We can do that with a binomial. We cannot do that with a continuous, right? So we can do exact things with discrete random variables. We cannot do exact values with continuous. We have to always be greater than, less than, or in between. And of course, whenever I say greater than or less than, it's the same thing as saying greater than or equal to and less than or equal to, right? So the equals part doesn't change it. It's the exact same value, because adding in that equals is just adding in nothing. Okay, so the standard normal curve, like the little picture on the right, is that perfect bell curve that we're all used to seeing. And it's just a very special version of the normal distribution where we have centered it at 0 and we've normalized it so that the standard deviation is equal to 1. We've basically, shrunk it or expanded it. So that's the standard normal distribution. And it exists so that we can have z-scores. That's all it is. The standard normal distribution is the visual representation of z-scores. Because when you talk about a z-score of 1, that means that data value is exactly 1 standard deviation above the mean. And so if we were on the standard normal curve, a z-score of 1 would actually land at the number 1 on the number line, because your standard deviation would be a distance of 1. That doesn't mean that if we don't standardize our distribution that we can't get a z-score of 1. We still get a z-score of 1 for something that's exactly 1 standard deviation above the mean, but the mean could be 300 and the standard deviation could be 10. So a z-score of 1 would correspond to the number 310 rather than the number 1 if it was the normal, right? The standard normal. So that's all the standard normal is. It's been standardized so that the mean has been shifted over to 0. And we have divided everything by the standard deviation so that now our new standard deviation is just 1. The properties of the standard normal distribution are no different than all other normal distributions. And that is that, the values to the left of something are smaller than the values to the right of something. But the big difference here is because it's been standardized, the values to the left are now all negative numbers because the middle is at 0, right? And values to the right are now positive, again, because it's been centered at 0. Of course, the area under the curve is still equal to 1 because it's still, a probability distribution, and that never changes. So here's a typical example where we can use SAS to calculate some things. For instance, we want to calculate the probability that z is less than or equal to 1.36. So when they're asking for z, then they're asking for a z-score. So that's when we put in our x value of 1.36. Because we're doing z's, we know we're on the standardized normal. So we put in a mean of 0, a standard deviation of 1. Then we run the code, and it's going to spit out 0.91, right? Because remember, the CDF is always the area to the left. So here's the picture to remind us what happens when we do a CDF. We get the area to the left. That's the probability of being less than or equal to 1.36. Now, if we needed to find greater than, well, that's easy. All we have to do is take 1 minus it, right? Because we know the greater than is going to be the other part. So we just do 1 minus that bit, and we get, the 8.69% or 0.0869. It's just that simple. If we want to find in between, we can do that just as easily by figuring out 2 different CDFs, right? So if we want to find the probability that something is between 2 numbers, all you have to do is find the area below the top number and then subtract the area below the bottom number. And you can see that you're left over with what's in between, right? Because if we do a CDF of 1.36, it's going to give us all of the area from 1.36 all the way down to negative infinity. Then if we do the z-score, right, find the CDF of negative 1.2, it's just going to give us this area in this left tail. And if we subtract that area from that whole big piece, you can see that what's left over is the in-between. So that's how we find in-betweens with SAS, is you have to do the top value minus the lower value, and that always gives you in between. Here's another simple example, right? X has a normal distribution, mean of 5, standard deviation of 2. Now we want to find the probability that X is greater than 7. Well, that's easy. We plug in 7, the 5, and the 2 into our CDF. We get a value of 0.84, but we realize because this is a greater than, we simply have to do 1 minus it. Now, here's a little trick. If you go into your code and you put a 1 minus in front of the CDF, it will do the math for you. So you don't have to do this. It'll just spit out that answer for you. So you can always change the code and do it that way. So again, if we wanted to find the area in between two things, you can see the green bit is the CDF of 2. It gives you everything below 2. So everything that's shaded in green is CDF of 2. Then you come along and you do the CDF of -1.5, which gives you just the stuff in blue. And you can see that if you subtract the blue stuff from the green stuff, you're left over with the black stuff in the middle, which is what we wanted because we just wanted the area in between those two. So that's how we do in-betweens. All right, so here's another simple example, right? So all we have to do is, okay, that's visually what we're trying to find. We can plug that stuff into our into SAS. We can get the two values. We can subtract the differences, and there it is, just a little bit over 4%. What about if they ask the question in the other direction, right? What's the weight of a package such that only 1% of all packages exceed this weight? Well, I always say you want to draw a picture. So here's a picture where we have a cutoff that has 1% above it, because that's what it means to only have 1% exceed, right? 1% being more. And once I have that picture, I now realize, okay, I'm looking for a value that has 99% of the area below it, because that's what I need, because the quantile function, just like the CDF function, is based on area below, right? Area to the left. So I have to give the quantile function the 99% for my probability, give it the mean and the standard deviation that they told us, you know, in the question, they told us it was a mean of 1, standard deviation of 0.1. We run that and we get, I don't know, I guess 2.33. I don't think they actually had the answer written down here, but it looks like, according to this, 2.33, which sounds about right. But in any case, it's really easy to run. Okay, the normal approximation of the binomial, we've already talked about this. We can calculate the binomial probability using the binomial formula. We can use the cumulative binomial tables. But when n is super large and p is not close to 0 or 1, i.e. it's right in the middle, close to 5, areas under the normal curve with a mean of NP and a variance of NPQ, i.e. a standard deviation of the square root of NPQ, can be used to approximate the binomial. So this only works when n is large, and it only works when p is relatively close to 1/2. And we've talked about that you have to do NP, you know, n times p, and then you have to do n times q, which is 1 minus p, and both of those have to be 10. So your p can deviate away from the middle, right? It can be closer to 1 or 0, but in order for both NP and NQ to be bigger than 10, your sample has to be really big, right? So it's a combination of the two. This is a silly thing. I don't know why we do this anymore, this whole approximation thing, but it's still used as a teaching tool. We have to talk about it. Just know that when we're doing this, we have to do what's called the continuity correction. And this is where we either add or subtract 0.5 to get a better approximation of the binomial. I don't think you should try and memorize when do I add and when do I subtract. The best thing is to just draw a simple curve. Label, you know, draw your little, so for instance, here's my normal curve. And they say, okay, approximate the probability that x is less than or equal to 4. This would be for the binomial, right? The binomial of less than or equal to 4, and then they want you to figure out what it is for the normal curve, right? So kind of think of like a z. What number should we put here to give us the more accurate answer? Okay, well, so let's just say 4 is right here. It doesn't matter where we put 4, but binomials, the bars are always centered on 4. So this upper edge is 4.5, and this lower edge is 3.5, right? Because it's 4, right? So you go up 1/2, down 1/2, because then the next bar would be snugged right up next to it, and it would be centered on 3, right? So if we want to know the probability that x is less than or equal to 4, that means we want to include this bar and then everything below it. So if we want the normal curve to approximate at best, we want the normal curve to stop at this upper bound of the last bar, right? The last bar goes from 3.5 to 4.5. So that means we need to do x is less than 4.5. And that's going to give us a better approximation. So that's, you know, to me, that's an easier thing than trying to memorize when to add and when to subtract. Again, here are those formulas for the mean if we have a binomial, we know if we take n times p, that gives us the mean of the binomial. And if we take the square root of NPQ, that gives us the standard deviation. Remember, Q is just 1 minus P. So in this case, P was 40%. So you can see that's why Q is 60%. And once we know those two things, we use those to create the normal curve that approximates, right? Because to do normal curve, we need to know the mean and standard deviation. So these become the mean and standard deviations of the approximating normal curve. So there's the binomial. There's the normal curve that approximates it. Oops. Again, we wanted everything less than or equal to 10. And because we're less than or equal to 10, we need all of the 10 column, right? The little part of the histogram that represents 10, and its upper bound is 10.5. So that's why we set the normal curve to be 10.5. And that gives us a more accurate answer than if we just, did 10, because we'd be missing half of that last bar. Okay, so the central limit theorem. This is really important. So when we're dealing with continuous random variables and we're dealing with these normal curves, the normal curve doesn't change at all if we're just sampling one thing at a time. Pick one person, what's the probability their weight is above this or their height is below this, that kind of thing. But if instead we go out and pick 10 things and then take the average of those 10 things and then say, what's the probability that that average is less than something, greater than something, or in between something, we now have to adjust the curve for that. And it's a very simple adjustment. The mean still stays the same, but the standard deviation of the curve gets adjusted, and you end up taking the original standard deviation of the curve and you simply divide by the square root of your sample size. So again, if you were trying to figure out the probability that a sample of 10 people had an average weight of blank or higher, right? Well, you would just take the standard deviation of your sampling distribution for people's weights, and you would divide it by the square root of 10. And that now gives you a new normal curve that is adjusted for samples of size 10. That's the central limit theorem. It really is just that simple, that all you're doing is taking the population standard deviation divided by the square root of n. And that gives you, the accurate estimator for things. So here's an example, right? Tires last 20,000 miles, standard deviation of 3,500 miles. What's the probability that a sample of 70 tires would have a mean less than 1950? Or sorry, 19,500. So here's our mean of 20,000. Here's our new standard deviation. It's the population standard deviation of 3,500 divided by the square root of 70. And you can literally type this in as you see it into SAS, because SQRT is the code for taking a square root. So down here for S, instead of putting 418.33, which is what this is when you round it in your calculator, you could have just said S equals 3,500 / SQRT parentheses 70 close parentheses. If you just put this exact stuff in there, it will calculate the standard deviation, and it will it will keep in memory a lot of decimals. So it'll be far more accurate than if you are rounding to 2 decimal places here. And in fact, I would say that you would always want to round this to at least 6 decimal places, because our answers should always be rounded to 4 decimal places. So anything else should be at least 2 decimal places further. So this, if you're going to do this, if you're going to type this into a calculator and then write that number in, you should give yourself at least 6 decimals. The quantile function, like I said, just works in reverse, right? It's basically like you've taken a z-score formula here and you're solving backwards. And sometimes you have to do that when you're dealing with sample sizes, right? So if you want to find how big a sample size has to be to get you a specific probability, well, you have to use the quantile function to deal with the probability. That'll work backwards and tell you the z-score that corresponds to that probability. And then what the mean and the standard deviation is. So now you got the z-score based on the probability from the quantile function. You have the mean, you have the standard deviation. So all that's left is you don't know the sample size, right? So that's where you just have to solve backwards for the sample size. And it takes a little algebra, but it's really not that difficult. So for instance, there's a question in the homework that asks us to do that, where they want you to find a K that, you know, captures 60% of our data around 250. And it's all based on using the Z-score formula, figuring out if you do the quantile function, you can figure out what the cutoff is that gives you the 60%. And then once you have that, it's just simply you're solving, you know, backwards for the missing piece. So it's pretty easy once you realize what you're looking for. And then the sample size question, that's one where we have to actually do a little math. We plug in everything we know, and you have to kind of solve algebraically backwards for n. And we can go over those more on Thursday after you guys have had a chance to try them all. Testing to see if something has a normal distribution. Excel has a way of doing it. It's kind of clunky, but you can find videos on YouTube that'll show you how to do it. And then of course, SAS has a really easy way to do it. And the notes are in the SAS how-to guide. All right, questions? All right, well, that's the last of the new material for this class. All you have left to do is this week you've got the homework set for week 5, and then next week is your final report. So are there any questions on either the homework or the final report that you guys want to go over? Otherwise, we can get out here early.
I can go. This is Christina. I can ask a question.
Go for it.
I think you've cleared this up for me, but on 4.88, so the first part is a binomial distribution, and I understand how to do that. It's a binomial function.
Yep.
And then the second part is the normal approximation.
Yep.
And I'm guessing that's where you use the standard deviation and the mean that you calculate using those equations.
Yes.
The question I have for you is that when I do the normal approximation, it gets it closer, but it's still not really close. Like the probability out of the binomial, I got 0.00590. I'm sorry, I can't even, my eyes are so bad, I can't even read how small this SAS prints it out. But when I do the normal approximation, it's closer, but it's not like. Yeah,
that's why it's more of a thought experiment.
Okay.
It's not something we do in the real world, right? So just so everybody understands, part A, you're supposed to have 2 answers to part A. You're supposed to calculate the probability that y is less than 5 using the binomial, right? That's what it says, compute the exact probability. You do that with a binomial. And then you want to do a normal approximation using less than 5. So you have 2 answers for A. Then you come back and you redo the normal approximation, this time with x equals 4.5 instead of 5, and you will see that it gets better. It gets closer to what the exact answer was out of the binomial. And why should this help? Well, it's because of that continuity correction thing that we're doing. Then for part C, again, you should have 2 answers for part C. You do the exact probability answer by doing the appropriate things in the binomial to get the answers between 8 and 14, right? Strictly between 8 and 14. Then you come back and do the normal approximation with the continuity correction, this idea of adding or subtracting 0.5 to find this probability on a normal curve. So you basically have 5 answers to this question. You have 2 for part A, 2 for part C, and 1, well, technically 2 for part B too. You have a numerical answer, and then you just discuss why it happened. So like six answers there. But a lot of students, I don't know why, they read that and they don't realize that they have to do 2 things for A and 2 things for C, both the binomial and the normal approximation. All right, anything else?
So I'm assuming this pi is p in 4.88, right?
Yes,
so
yes.
P is, yeah, it's like sometimes they use one, sometimes they use another one.
Yeah.
So when I did it, mine is coming out to be probability is 0.02. And I think I heard Christina says 0.05, so I don't know what I'm doing wrong. So I have n factor 20, probability 0.5, and x is 5.
Yeah, so for this one, it should be n is 20, p is 0.5, and then if we're doing the binomial, x should be 4. You should do a CDF of 4, because if you want to be strictly less than
Okay.
5, you're only adding from 0 up through 4.
Got it. That's what I was doing wrong.
Yeah.
Okay.
Oh, sorry, you said we should do a CDF of 4 on that one?
On the binomial, yes, this part A here would be a binomial CDF with 20 comma 0.5 comma 4, right, where it's n p x, I think that's the order you put it in. I can't remember, but in any case, x is 4, because if you want to be strictly less than 5 in a binomial sense, right, in a discrete world where you're counting things, if you have to have less than 5 children, you can't have 4.5, right? You have to stop at 4. So
Right.
so x would be 4.
Okay, thank you.
Yep. Anything else?
And then, I'm sorry, can you explain it one more time? So even if we did the approximation with 4.5 in normal distribution, it is still not closer to the binomial probability.
Well, it gets closer, but it's not perfect, right? So so for part A, the second part, when you do the normal, you would do the normal CDF, and the mean, right, would be 10. The standard deviation is the square root of 20 times a half, which is, I think, let's see, that's 10, that's 5. So it's the square root of 5 is going to be your standard deviation. And then when you're trying to approximate this, your x is 5, because you want the area, less than 5. So in the normal curve, you do less than 5, and you'll see that it's not close at all. But then for part B, you go, okay, let's change this and do 4.5, because we know that the binomial, to be less than 5, we start with the 4 block, right? And then we've got, the 1 for 3, the 1 for 2, and the 1 for 1. Well, to make sure that our curve stops and captures the entire 4 block, it has to stop here at the upper bound, which is 4.5. So that's why we change it to 4.5, and we rerun it with 4.5, and we get an answer that's closer. It's still not great, but it's closer, right? And the reason why it's not great is because we can only approximate the binomial with the normal curve if n times p and n times q are both 10 or above. Well, if our p is 0.5, that means q is also 0.5, right? Because q is always 1 minus p. So n times p is exactly 10. N times q is exactly 10. So this is basically as small as our sample can get in order for the approximation to work at all. The larger the sample gets, the better the results get. So with such a small sample of 20, it's going to be a rough approximation. It ain't going to be great. Anything
Okay.
else?
I have one more question on the last question, which is around the quantile plot. So I know how to do that.
Yep.
I guess my question on that is, I'm guessing the normal test statistic gives you the goodness of fit. The p-value tells you the statistical significance.
Correct.
So if the if the test value is closer to 1, that means it's a better goodness of fit, right?
Well,
But,
1 or -1, but yes.
yeah, but I mean, but then the p-value, when I ran this, is not statistically significant. So does that mean it shows it's a goodness of fit, but it's a not statistically significant goodness of fit?
The p-value on the quantile plot is actually a little weird. It's not necessarily the same kind of thing.
Okay.
It's odd.
It threw me because I'm very familiar with p-values. We use them all the time in healthcare research. I mean, so when I saw this and the p-value isn't anywhere near, at least the answer I got, I mean, it's nowhere near statistical significance.
Right, but see, this is where it's confusing. You're right that it's not statistically significant, but it's not statistically significant in order for us to be able to reject the null hypothesis. And with this test that we're running, the null hypothesis is that it's normal, that things are the way we think they should be. So you would basically say that it was bad if it was significant. So if your p-value was really, really small, that would make you think that it's not necessarily normal, right? That it doesn't come from a normal distribution, because that's what a quantile plot does, is it tells us whether or not the parent population is approximately normally distributed.
Okay.
So the null hypothesis is that it's normally distributed. So you want to get a large p-value because you don't want to reject that null. So that's why, because otherwise it wouldn't make sense that you would have such a strong R value and such a big p-value, right?
Yep. Okay. Because that threw me, because I mean, there's clearly a linear
Yeah.
pattern to the data. And okay, that threw me. That makes sense. I think the null hypothesis stuff is like statistical theory, right? And I was just trying to, that makes a lot of sense now that you said it that way. I was just trying to understand like why the p-value would look like that.
Right.
When I can clearly see there's a linear pattern. Okay.
Totally. Yeah. Because we don't really cover hypothesis testing in this course. So that's why that p-value can be a little misleading. Anything else?
I haven't done 4.94. I only have 2 left. So I'm assuming we have that function in the SAS stuff, right? So we should be able to use the SAS to do that last question.
Yeah, there's the quantile plot. We actually did one early on.
Yeah, it's under week 3. Got it.
Yeah, there it is. Yeah. So it's really easy to just go in and get it from the menus. If you wanted to, there's a coding option, but I had this coding option here first until one of my students went, "Hey, dummy, I figured out how to do it in the menus." I was like, "Oh, well, crap, I'm gonna put that in there too." So now that we know how to do it in the menus, I don't think anybody's going to use the coding option, but I just left it there just in case. Anything else?
One last question, and I promise I'll shut up.
No,
On
go
the
for it.
final project, section 3, I know you said we're not going to have a presentation.
Right.
But the last part, can you just kind of walk us through what you're looking for on that?
Are you talking about the probabilities part?
No, it's like section 3 where you have to make up like a hypothetical data
Oh, yeah.
question. Yeah.
Okay, so section 3 is basically your opportunity to kind of do a dry run, rough draft of your dissertation. So the idea is to discuss some aspect of your dissertation that involves a variable, right? And it says, are they continuous? If it's a continuous variable, all the better. But if it's not, that's fine. Like some people are doing, they're not even collecting real data. They're just doing qualitative stuff, right? So they're not even going to be able to analyze means and things like that. That's fine too. So describe the setting in your problem scenario and a short background information. So this is basically like what you do in chapter 1, where you describe what's the problem that I'm going to try and fix. And so you're defining exactly what you want to solve, right? So 1 and 2 is basically stating the problem, kind of talking about maybe what's been done in the past briefly. I mean, I'm not looking for a friggin' lit review, right? Just a quick, couple sentences, paragraph or 2 at most of, here's the problem, here's some things that have been tried in the past, and you know, and whether or not they worked or didn't work. Here is what I am proposing as a new or better solution. And then here's the kind of data that I would need to collect in order to test my new proposed solution, and describe all of those variables, right? So you might be collecting more than one variable. So when you talk about data, you're talking about the entire set of data. When you talk about the variables, you're talking about the specific things, you know. So like, I need to, you know, collect vital signs from a bunch of patients. Well, the variables are going to be height, weight, blood pressure, you know, blood oxygenation levels, you know, whatever it happens to be. And then for each of those, okay, so height's continuous, weight's continuous, blood pressure is continuous, blood oxygen is continuous, right? All that. So that would be, you know, what you're doing with describing it. And then you describe the statistical methods you're going to use to analyze your data. So again, referring back to what you're trying to solve, describe how you would analyze the data in order to test whether or not your solution is correct. And those analyses could be basic things like summary statistics, or they could be more advanced things like hypothesis tests and regression analysis and whatever it happens to be. That's fine, right? It doesn't have to be held within the confines of what we've learned in this class so far. And then that's it. That 1 through 5 is based on all that. 6 is completely separate. So 6 is where, because the idea is hopefully with all of this, one of your variables was continuous, and one of the things that you wanted to test were probabilities, because then that leads you into question 6, but that you don't have to do that. I want you guys to do 1 through 5 and make it fit your dissertation. Mr. Falcon.
Yes, sir. So I was just wondering, like in my case where this final paper, or at least the topic at this point is leaning towards improving engagement, right?
Yeah.
How would I make that from a variable perspective? I don't even know the measure of engagement now, because that's something that I'm still going to spend more time on, measuring engagement. So I'm wondering how I'm going to do this to make it fit.
Well, you could either spend some time and figure out some feasible ways to measure engagement and then use that scenario, or you can just make it up and say, I'm going to have an engagement scale that's going to be based on, you know, blah, 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 and go from there. Because this is all just make-believe thought experiment kind of stuff. So, you know, nobody is collecting any real data. Nobody is analyzing any real data. This is basically just getting you to think about the process of how you're going to build out your dissertation. So it's getting you to think about the steps that you would then take for real later.
Got it. Thank you.
Yep.
What about if it's if there's a qualitative portion where there's an actual survey, like Likert scale?
That's fine.
Asking people for engagement.
Yeah, that's fine.
Okay.
Yeah, absolutely. That's totally fine. You know, because obviously for number 4, you would just say, no, it's not continuous, right? It would be, you know, if you're doing Likert scale stuff, then it's not even ratio level data. It's only ordinal level data. So, you know, when you describe your variables, it would be, you know, this variable would be ordinal level discrete data, you know, that kind of thing, or just ordinal level data. We really don't even talk about ordinal level data as being anything other than ordinal. We normally only talk about discrete and continuous once it gets to ratio level, because everything below ratio level by definition is ordinal, because it's discrete, because it's just this, or this, right? There's no measurement. You're just counting crap. But we normally don't even talk about them being discrete or continuous. We just talk about them being ordinal, nominal kind of thing. And so you can just say, oh, it's just good. It's going to be ordinal level data, and you're done, right? Are they continuous? No, because it's ordinal level, dummy. Of course it's not continuous, right? It's that kind of thing.
Thank you.
Yeah.
So can I ask a question? And this is like very early on for me. Like I'm not really at my dissertation topic yet, but I'm in a certain space, I guess, around digital therapeutics. But one of the things that I want to do is actually correlate patient engagement activation with physiological changes,
Sure.
biometrics and other things. So those would actually both be dependent variables, right? Because the hypothesis is that the digital therapeutic drives engagement and that better engagement has an impact on physiological scores. So like in that sense, what I've looked at is a patient active, it's called the PAM, it's a patient activation measure. That's actually that would be a discrete variable. Obviously, if I was measuring like hemoglobin A1C or blood pressure, that's going to be continuous.
Sure.
So is that, I mean, that you can have that, right? You can have a discrete.
Oh,
And
yeah.
okay.
Yeah, absolutely. If you're trying to find a correlation between a discrete variable and a continuous variable, you're just going to be doing things like logistic regression instead of regular regression. So yeah.
Yeah. Okay. Okay. So we do have to do 6 through, you want the rest of that in there, or you just want us to get through 1 through 5? Are you looking for all of that?
Well, so 1 through 5, I want you guys ideally to try and do 1 through 5 in terms of your dissertation. And now if you're not far enough along that you have any idea at all what you're going to do your dissertation on, then I would suggest just pick a topic, pick a problem and a solution to a topic that you're interested in, that it might be at least tangentially related to your dissertation, so that this isn't just a complete waste of your time, right? When you get to part 6 does not have to be related to 1 through 5 at all. Part 6 is basically just a rehashing of the homework. If you look at, here it is. So homework, right? What's the probability that something is greater than something? What's the probability that you're in between two somethings? What's the probability that you're less than something? Well, that's exactly what here is, right? I want you to describe how you would calculate the probability for a continuous random variable is greater than a specific value. Oh, is less than a specific value. Oh, is between two specific values. Oh, percentiles. Oh, right. This is all this is you describing how to do your homework. What's the process to do this? And then you have to find a way to get graphs of it, right? So if you're doing all this in SAS, you're not going to have graphs. You're going to have to go out there and find an online tool that will graph these things for you, or just draw it by hand. I mean, you can literally just draw a graph for each one, draw a little bell curve, label it, and shade it in. Now, when it talks about greater than a specific value, you can pick whatever value you want. You can pick whatever mean and standard deviation you want, right? So you're basically doing all of this. You create your own scenario, basically recreate a homework question with your own scenario with a mean and a standard deviation, and then give yourself, okay, this is how I would calculate the probability of picking a random thing and it being greater than 275. This is how I would calculate the probability of it being less than 150. This is how I would calculate the probability that it's between 200 and 250. This is how I would calculate the score that gives me 10% of the data above it. And here are the graphs for each of those 4 things. So that's what you're doing with part 6. And then the rest is just, kind of just describe and justify what you're doing as you do it.
Okay. But we could take a hypothetical, because like one of my variables would be continuous. So I could create a hypothetical. Okay.
Yeah, if you have a continuous variable that you're going to be working with, then by all means use it. Make it part of your hypothetical. Otherwise, just make something up.
Okay. Got it. Thanks.
Yep. Anybody else? All right. Well, I think that was a good session. I think we all know what we need to do. Now get out there and do it, and we'll see you on Thursday.